For separations of 50-50 propene-propane mixtures, I compare the experimental breakthroughs obtained experimentally with 4 different MOFs: Caust 7, cobalt gallite, LTA 5A zeolite, and nickel MOF 74. All these experiments were performed at a total pressure of 100 kilopascal and 298 Kelvin. We note that all 4 MOFs are selective to propene, and propane is rejected into the gas phase during the adsorption cycle. We also note that the dimensionless concentrations of propane attains values larger than unity and approaches a value of 2. But the extent of the departure from unity depends on the particular MOF. The phenomena observed here is termed a rollup, and this is usually experienced for the component that is less strongly adsorbed within the pores. The x-axis I use here is a modified time parameter that consists of a product of Q naught, the volumetric flow rate at the inlet in liters per second, times the actual breakthrough time in seconds, divided by the mass of adsorbent in the bed in kilograms, and the units of the x-axis are liters per kilogram. In my presentation today, I examine the variety of factors that determine the extent of deviations of the phenomena called a rollup that is experienced for propane, the less strongly adsorbed component, and I show that the extent of rollup depends on a variety of factors that include the composition of the feed mixture, the diffusional influences within the pores of the metal organic framework or zeolite, the contact time between the crystals of metal organic framework or zeolite and the gas phase in the fixed bed adsorber. In order to investigate the variety of factors that influence the extent of roll-up phenomena, I examine separations of mixtures of propene and propane at 353 degree Kelvin and 2 bar pressure in a fixed bed adsorber packed with Chabasite zeolite. And I undertake transient breakthrough simulations to investigate the different factors that influence the extent of rollup. The background theory is described in my paper that is cited here. Watch also my video presentation on transient breakthrough simulations on my YouTube channel. Here's the structure of Chabasite. Consists 1 unit cell of Chabasite has 6 cages. Each cage is separated from an adjacent cage by narrow 8-ring windows. The cage volume for Chabasite is slightly larger than for DDR zeolite, but significantly smaller than for fungicide. The feed mixture composition has an important influence on the extent of roll-up that is experienced. For adsorption of mixtures of propene and propane in Chabasite zeolite, the equilibrium data shows that the component that is most strongly adsorbed is the saturated alkane, which is propane, due to higher polarizability, and the first component of breakthrough is the unsaturated propene. The roll-up for a 50-50 mixture is of the order of 2. In other words, the dimensionless concentration at the exit of the fixed bed approaches a value close to 2 for 50-50 mixtures. For mixtures of propene and propane in the proportion 90:10, the roll-up phenomena is negligible, and the extent of roll-up is only about a factor 1.1. In these simulations, the intracrystalline diffusion limitations are considered to be of negligible importance. The x-axis is the modified time parameter, consisting of the product of Q0, the flow rate at the inlet in liters per second, times the times in seconds divided by the kilogram of Chabasite in the packed tube. The units of the x-axis is liters per kilogram. Let's now examine how intracrystalline diffusion influences the extent of roll. Chabasite zeolite, suggested as an adsorbent for propene-propane separations, with a cage-type zeolite where adjacent cages are separated by windows which are 4.2 angstrom in this direction and 3.8 angstrom in this direction. Due to subtle differences in the bond angles and bond lengths between propene and propane, the ratio of diffusivity of propene to propane is a few orders of magnitude high, as reported in this paper by Ruswin and Reyes. And therefore, due to the high ratio of diffusivities, it is possible to construct a kinetic separation scheme for propene-propane separations. In order to investigate the influence of intracrystalline diffusional influences on the extent of roll-up, we carry out transient breakthrough simulations in a fixed bed of length 0.3 meters with a packed bed voidage of 0.4. The superficial gas velocity at the inlet is 8 millimeters per second, yielding a interstitial velocity of 20 millimeters per second. The contact time between the gaseous mixture and the crystals of Chabasite zeolite is L divided by V, which is 15 seconds. The ratio of the Maxwell-Stefan diffusivity of component 1 to that of component 2 is taken to be 5,000 based on the experiments of Ruswin and Reyes shown on the foregoing slide. The Maxwell-Stefan diffusivity of component 1 is 1.7 10 to the minus 12 square meters per second. We vary the diameter of the radius of the crystals, and with increasing values of RC, we examine the influence of the diffusional influences quantified by the parameter d sub 1, which is the Maxwell-Stefan diffusivity of propane, to the square of the radius of the crystallite. For the breakthrough simulation shown here, the value of d1 divided by RC square is 6.8, 10 minus 2. With increasing crystallite radius size, the value of d1 divided by RC squared decreases in value till a value of 1.7, 10 minus 4. We see that with increasing diffusional influences, the breakthrough of propane occurs earlier than that of propene. And also we note that the extent of roll-up experienced by propene decreases progressively with increasing diffusional influences. So diffusional influences have two effects. The extent of roll-up for propene decreases, and furthermore, propane breaks through earlier than propene. Therefore, we conclude from these simulations that the extent of diffusional influences have a very strong influence on the sequence of breakthroughs and also the extent of roll-up of propane. In a second set of transient breakthrough simulations, we maintain the value of d1 divided by RC squared, where d1 is the Maxwell-Stefan diffusivity for component 1, which is propene, at a value of 1.7 10 minus 4 per second. We vary the flow rate of the gaseous mixture at the inlet, and thereby we vary the contact time between the gaseous mixture and the crystallites of Chabasite zeolite. The contact time is the length of the fixed bed L divided by the interstitial gas velocity V. The simulation here is for a contact time of 30,000 seconds. This is for 3,000 seconds. This is for 300 seconds. And this is for 15 seconds. We note that the extent of roll-up for propene is significantly influenced by the contact time between the gaseous mixture and the crystals of Chabasite zeolite. With decreasing contact time, the extent of roll-up decreases in value from 1.4 to a value that is close to unity. Furthermore, with decreasing contact time between the gaseous mixture and the crystals, the breakthrough of propane occurs earlier. Indeed, the influence of decreasing contact time is analogous to the influence of decreasing values of the parameter d1 divided by the square root of the crystallite radius. So in summary, the extent of roll-up that is experienced in a fixed bed adsorber is influenced by a variety of factors that include the extent of diffusional influences, quantified by the parameter d1 divided by the square of the crystallite radius, the contact time between the gaseous mixture and the crystals, and the composition of the feed mixture.